Homework assignment 4, thanks to Nathan for notifying me that that wasn't right, has been updated. It had asked for you to apply one of the other forms of particle filters besides the simple version that we've all been working with. We used either linearization, auxiliary particle filters, which we haven't talked about yet, but we'll be going over today, or something called Viterbi particle filters, which we also haven't talked about yet. And so it was really inappropriate. And I updated it on Friday, and what I asked you to do is to apply it to a real problem that's in multi-dimensions. And I did that at the time, expecting fully that I was going to have a new set of slides on multi-dimensional sort of case studies, showing examples of problems where I've applied it and going through and showing how the particle filters worked, which aren't actually ready. I wasn't able to get them done for today's lecture. I'll have them ready, at least some of them ready, on Wednesday. I'm inspired by some of the sleuthing and code optimization that you all have done, especially you, Reed. And so I'm writing a generic function that can implement the various forms of particle filters, even for multi-dimensional state space models. So it's not ready yet. We're talking about auxiliary particles today, but I'm asking all of you to find a multidimensional problem for the homework assignment. And one of the things I'm looking for that we haven't been doing in the class very much is looking for a problem that is physically meaningful to you. Most of you that have been doing this on the homework assignments, you've been able to do it. But in the examples I've been going through in class, we've got the one car problem that was a little bit contrived. And I'd like to transition to working not only in multi-dimensions, but also with real data, or at least real applications, even if we're working with synthetic data. So, so I'm still asking you to do that for homework 4. And I want to just move ahead with that. The only wrinkle that's different... Okay, so I just asked the question, just for those of you that are listening, do you have to work with real data for the project, or can it be synthetic data? It can be synthetic data, but one of the things I'm hoping that I've been able to attain with graduate classes in the past is that students, the quality of the projects is often good enough that students can actually publish on it. And I think it would be hard to publish on synthetic data, on tracking in synthetic data. I mean, just because the standards are usually higher. They're like, well, anyone can track with synthetic data. And you also encounter the most interesting things happen when you work with real data and you realize, oh, there's always those aha moments. And it usually has to do with mismatch between what you thought you were working with and your model of the process and what the process is actually doing. I mean, there's usually surprises that occur. And you miss out on that when you're working with synthetic data, because then the model that you use in the tracker and the model that actually generated the data, there's a perfect match. And so it's also not as good from the standpoint of understanding what are the consequences of tracking with a model that is not representative of what actually generated the data, and beginning to understand those model errors. So I discourage it, but it is allowed.
Well,
Sam?
you could still play around with mismatches just by intentionally changing the process model that you use to create the synthetic data and what you use.
Yeah, it's true. It's true. Usually, though, the way that you imagine that your model is inaccurate and the way that it's really inaccurate from real data is quite different. But I mean, it's the surprises, I think, that are interesting that really come from studying and working with real data. So, yeah, again, it's a good point. You're right. You can study it, at least specific types of mismatches, but my preference would be for you guys to work with real data.
It's a known mismatch.
A known mismatch. That's a good way of expressing it, yeah. Good. Are there any other questions about the projects or anything else before we begin?
I was just a little curious when you were talking about the kernels and the bumps.
Yeah.
Is the posterior distribution dependent on what bump you pick?
No. Our model of the posterior is the same as what I had written on the earlier slide. Try it again. So the model of, I'll write the joint. And we've got this sum of impulses that are weighted and are located at where our particles are. I ran out of room that time. So we've got, that's supposed to be a minus sign. So we have this poorly written weighted sum of impulse functions, and this is our representation of the posterior. Those kernel density estimates are really only for the purpose of displaying this. It's only a way for us to look at it, rather than trying to look at the individual particles and see what their weighting is. It's a little bit like in a single dimension, at a single point in time, I was showing if you've got a Gaussian distribution, our representation are these impulses that are located at various points and have various heights. And that's hard to look at, especially if you're trying to look at an image, to look at these very sharp vertical spikes. And so the kernel smoothing, the only purpose of the kernel density estimation was to smooth that out. So it's a well-behaved function that we can look at and visualize. But that's all. It is not the representation of the posterior itself. The representation are these impulses, which is expressed by that equation.
I'm a little confused because it seemed like that we were trying to get at the what the posterior looked like. In fact, by the impulses themselves were a representation of something that we could look at in a kind of continuous fashion.
Good. Almost.
The interpretation is where I'm a little confused on that.
It's a good question, and it's an easy thing to confuse. Ultimately, what we're interested in tracking problems is estimating the state. And we can estimate the state without ever directly estimating a smooth function of the posterior. And so we don't actually need this. We use it for visualization because it gives us insights, but we don't need it in order to estimate the state or in order to estimate percentiles. So there's a lot of information that we can get from directly from this abstract representation of impulses that that's just fine, that works, where we don't need the smooth representation. And ultimately that is what we're trying to do. Does that make sense?
Sort of.
So the kernel smoothing was, the kernel density estimation, it was just a visualization technique. I mean, that's all it was. That wasn't really what we're trying to estimate. It's the state that we're trying to estimate, and what our uncertainty is about the state. Got anything else, guys? I went a little bit fast at the end of the homework presentations last week through the linear filtering. Did you guys have any questions on that linear prediction technique for having a better importance density? It was one way of actually using the measurements to propagate our particles forward rather than letting them just scatter according to the process model. Is that more or less intuitive? Enough? Okay. I know that was last week, so those questions probably aren't fresh. I'm sorry? We'll come back to it through the homework presentations, because I expect at least one student will choose that as one of the improvements over the simple particle filtering algorithm that we had talked about. So we'll see it in that context. And I may use it in some of the case studies. I haven't decided yet. So, all right. Well, given that, so today we'll talk about the so-called auxiliary particle filters. That you need to know about is as follows. Our representation of the state at time n, and really we've got the entire, let me write it this way, 0 to n. We represent this as a sum of the weights at time n for each particle times essentially the delta function. I'm not doing this right.
It seems like don't you want the probability distribution? That doesn't make sense to me.
Yeah, that's what I want. Thanks. That's not going to work. It's testing the limits of how well I can operate this thing.
I did. Oh, the first one or the second one?
The second.
No, I think the second one. Sorry.
All right, let me try it again. So P of x
computer now.
That works. Yeah, I have class at 4:30, so I'm around until after that.
Mesh. Gosh.
Okay. Let me write that down so I don't forget. 3, you said? I said, Franco.
I'm about ready to give up and just go to the board.
Is that pronounced right?
Let me try this again, guys. So the probability of the entire trajectory, 0 to n, given our measurements from 0 to n, we represent as this weighted sum of impulses, where we've got the weight at time I, or time n for the ith particle, times, and then we've got the delta function of x of 0 to n minus that of the particle. And one of the slides I had said that this isn't what we actually need. It's not the marginal distribution that you plot. The marginal distribution that we were looking at images of was that at time n. And normally it's very difficult to obtain the marginal posterior from the joint posterior. But when you've got this representation as a sum of impulses, it turns out to be trivial, and it ends up being equal to just the sum of the same weights times the delta functions located at wherever the particles are at time n. And the problem that you're going to run into when you work on a multidimensional problem where your state is of dimension more than 1 is now you'll have this weighted combination of impulse functions that are also in multiple dimensions. But it turns out that if you want to look at the marginal distribution of just one element of the state, you can integrate out all the other dimensions of the state. This is still a multidimensional impulse function, and extract out the one that you're interested in. We don't normally have to refer to the element of a state, so I don't even have an indexing way of representing it. But let me represent it this way, because this is what you'll need for the homework, I think. Xn of, let's call this the jth element. So Xn of j, again, given the sequence of measurements that we've had, but now rather than looking at the marginal of this entire vector, we're looking at the marginal of just one element of that vector now. So this is now a scalar.
And in general, the jth element will depend on all the y's, and so, right?
Yeah, absolutely. Yeah. I mean,
the y's could be have components too.
I'm sorry, the y's what?
The y's will have components too. They could.
Yeah,
They
the
could.
y's will, and this is the entire past sequence,
Yeah.
past all the way to the current of measurements, and these are vectors. So at every, or at least they could be. So at every time sample, you get a vector, and this is the entire collection of vectors over the entire past through the present. And so this also, as you would expect, is still the same weights. But now it's just that element, the jth element, minus, and then again the particles for jth element. There, I think I fit it. So does that make sense? It took me a long time to write, but I think it's a fairly simple idea. It's very similar to what we did before implicitly, but then we didn't have to go to this step earlier because the state was already a scalar, and so we didn't have to think about this. But this is how you can look at it for individuals. This doesn't show you what's going on in terms of how the different elements of the state vector are correlated with one another. They may be very correlated with one another, and this doesn't show that. This is just sort of a one-dimensional view of what's known about each element of the state vector in isolation of the others. But nonetheless, that's one of the things you'll need. So when you're working with multiple states, and I'll show some examples of this on Wednesday as well, you should probably go through and generate one image for each element of your state vector, assuming it's not too large, and assuming that the elements are themselves meaningful. And again, I'll try to show some examples on Wednesday. So are there any questions about that? Okay, good. I'm really looking forward to it. It's exciting to me that this early in the term we've gotten to a point where we've got something that's useful, and you're at a point where you guys can apply it to real data and really start to work with it. This should give you a good head start for your projects. So I'm looking forward to see what you guys do with it. I think I will go back.